One of the first fractal geometry sessions at the CMS in a long time. It's been a long time since I can't remember when the last one was. So today I'm talking about a simple two-parameter family of iterative function systems. This is joint work that I've done with Nikita Sidorov. So we'll start very basic. I suspect everyone in this room knows exactly what an iterative function system is. It's a very classical way to construct a fractal. There's Sierpinski gaskets, ferns, Sierpinski sponges and such. The formal definition is you've got a bunch of linear contractions, and the iterated function system is the unique set K so that K is equal to the union of the linear contractions at K. There's multiple different ways to define it, but this is probably the easiest. And it turns out K is actually a unique attractive fixed point if I think about this as iterating a map of taking a set, taking it to the union of the contractions of the set. So simple example that most people have seen, you take the Sierpinski triangle, you shrink it by half in the vertical direction, shrink it by half in the horizontal direction, put 3 copies of it, and this, when you iterate the process, gets the Sierpinski gasket. So what I want to look at now is, it's a very, very simple family. It's going from R2 to R2. I'm having a matrix M times our vector B, so it's simple contraction, and plus some vector B1. And I'm going to use the exact same matrix for both types. So despite the fact I'm using only really one matrix and 2 different vectors, there's a lot richer structure in this than you'd think. Turns out, I mean, if these maps are going to be contraction maps, the eigenvalues of M have to be less than 1 in absolute value. And if there's less than 1 in absolute value, there's only a couple cases. They could be complex eigenvalues, which is coming from A plus BI, A minus BI in the first case. We could have, well, up to similar matrices, we could have 2 distinct eigenvalues, and it's actually convenient to differentiate between the case where they're both positive or one positive and one negative. If they were actually both negative, it's the exact same thing as they're both positive. So you don't need to worry about that. And the last case is when you only have one eigenvalue, but it's sort of a Jordan block sort of form. So there's really 4 cases on this. First one has been studied by a large number of people, going all the way back to 85. Despite that, there's still a lot of stuff that's still being discovered about these sort of maps. The second one, where lambda and mu are both distinct eigenvalues, and they're both strictly between 0 and 1. This is what started Nikita and I on this investigation. We actually continued on to look at the other cases afterwards, and the other 2 cases I listed there. So to give you a feel for, okay, some notation and discussion I'm going to be using a lot throughout the talks is I'm going to call these cases, I'm going to give them different names. The first one is going to be the complex case, because it's got 2 complex eigenvalues. The second one I'm going to call the positive case, because it's got 2 positive distinct eigenvalues. The third is the mixed case, because I've got 1 positive eigenvalue, 1 negative eigenvalue. And the last is the Jordan block case, because I have a Jordan block with 1 eigenvalue. So I didn't quite do them in the same order. So the positive case, I've listed 2 possible fractals that you could get from this. And there's a lot of other ones we'll see later on. The mixed case, completely different feel to what the fractal looks like. The Jordan block case, it's actually not as much variety with the Jordan block. The mixed case and the positive case, by changing the lambda and changing the mu in various ways, we can get a lot of different objects. For the Jordan block case, you've only really got 1 parameter to play with, so you don't get that much. And the complex case, again, I listed 2 different possible ones there, and it depends if they're relatively small, you can get something completely disconnected. If they're relatively big, you've got something with a whole bunch of interior. So just want to look at the positive block case a bit more carefully. So I've listed 3 possible iterated function systems here. And here I had lambda equals 0.55 in all of them, and mu equals either 0.7, 0.8, or 0.9. And actually 0.8, there's a bit of a cheat. It's not quite 0.8 because it's going to have some properties that I want to look at. If I look at the first one here, this iterated function totally disconnected. So this actually means, despite what it looks like, this is a whole bunch of dust-like points. So at no point is this, like the blue, the one map here, the one map takes it to the blue, the other map takes it to the green, because those aren't connected. None of the maps are connected, none of those maps are connected. These are completely dust-like. The second one, it is actually connected. There is a point here of the blue that meets a point of the green. So it's connected. It's not simply connected. There's a huge number of sort of circular holes in there, and it definitely has no interior to it. It's got no part where there's actually any substance. And the last one, it's going to be connected. Not only is it going to be connected, it's going to have interior. And the way we actually show it has interior is we actually show that there's specifically a ball around 0, 0 that is contained within this iterative function system. So the questions we're asking is, we've got a map, or we've got this matrix. It's got two eigenvalues. For what values of these eigenvalues is the iterated function system disconnected, and hence totally disconnected? For which values of the eigenvalues is it connected? For which values is the iterative function system have interior? Actually, we cheat here because it's easier to say, does it contain 0, 0, or does it contain a neighborhood of 0, 0? It's not quite the same as saying, does it have interior? But if it contains a neighborhood of 0, 0, it definitely has interior. I have no idea if there's an example the other way around, where we have an IFS with just this simple construct where it has interior but does not contain 0, 0. And the last thing we're thinking about is, for what point, or what can be said about the set of points where there's just one unique address? And I'll get back to this more later on when I actually want to discuss what I mean by unique address. So, just realizing I have no idea what time it is. So which points does the iterative function system contain a neighborhood of 0, 0? Which, if it contains a neighborhood of 0, 0, it will have some sort of interior. Turns out there was a result back in 2014 that explicitly said, if I can find a polynomial with some magical properties, which I'll go into a bit more detail in a moment, then their 0, 0 is going to be a neighborhood of the IFS. So what they end up doing is they somehow take this polynomial, they take a point arbitrarily close to 0, 0, within some epsilon that's explicitly computable based on the polynomial, and they somehow iteratively construct exactly what its expansion should be in terms of which maps to use when to get this point. So we need this polynomial to have a root at 1 over lambda, 1 over mu, have the property that all the coefficients when I add them up are strictly less than 2, have the property that b1 and b2 are equal to 0, and have that b0 is not 0. And if we have all those properties, then we can find a neighborhood of 0, 0, and using that as a corollary, they had shown that if lambda is, in the positive case only, if lambda and mu are between 0.953 and 1 and distinct, then you had a neighborhood of 0, 0. So we looked at this proof, and we made some changes to it, like we changed the authorship, but we also we also crossed out that bottom third line. It don't actually need it, but it's more there's some other things that I didn't quite mention here, but I can deal with the case where lambda equals mu, which is the Jordan block case, in which case it's not actually p of 1 over lambda equals p of 1 over lambda. It's actually p of 1 over lambda equals the derivative of p at 1 over lambda equals 0. So that's how you deal with a double root. Just make sure that you have, it's actually a double root of the polynomial. And with a more careful construction of the polynomial, we can improve that down for the positive case back from 0.953 to 0.832. We get it a lot lower. In fact, we get a much stronger result than that. In fact, we can do the positive case, we can actually do the negative case, and the negative case is much tighter. If lambda and mu are basically 1 over root 2 to 1, then we're fine. and the Jordan block case if lambda is bigger than 0.83. And in all these cases, the proof was completely constructive in that we said, here's a polynomial that works, and the polynomial is parameterized by lambda and a mu, and it has the properties we want. And in fact, the strange sort of boundaries we get, which I'll show in a moment, is coming from the condition that the sum of the coefficients equals 2. So that's how you would show if it has interior. What about if it doesn't have interior? Well, one way to show it doesn't have interior is to show it's totally is to show that it's disjoint. So let's think about the convex hull of an iterative function system. This particular iterative function system I draw as a positive case. The same sort of techniques will work for the negative case and or the mixed case and the Jordan block case. And we have the property that if 0, 0 is not in the image of K and the image of K2, then it can't contain the neighborhood of 0, 0. For example, here, I've got my map. Well, 0, 0 is in this convex hull, this convex hull. It may be in the K, it might not, we don't know. This one, it actually is sort of on that boundary. This particular one here, 0, 0 is definitely not within the image of K or the image or the other image of K. So if it's not in either image, it's not in K. But there's nothing special about K. Nothing special about the convex hull of K. I could have used the first iterate of it and looked at the second iterate of the map, or the third iterate of the map. And if you can do this, you can automate it, put it on a computer. So here's a map where here lambda is going to be between 1/2 and 1. This is the positive case only. Very similar maps happen for the other case. Here lambda mu is between 1/2 and 1. And in this case, based on a first level iteration of what K is in its convex hull, all these points with a relatively small lambda and mu do not contain 0, 0. Based on the polynomial, all of these points up here do contain 0, 0 as an interior point. But as I said, there's nothing special about which K I used. I could iterate and get a more detailed K or a more complex K. And if I do that, I get a more complex picture of things that I know do not have interior. And I can iterate, I think this is a 5th level approximation of K iterating 5 times. Or I could iterate it 10 times. Or I could iterate it 15 times and start really grinding the computer down. And this set, we didn't actually prove this, but this set is going to be probably going to be disconnected. Like there's going to be regions where we don't have interior that are disjoint from the main body. But the interesting thing there is all the white in the middle, we still don't know. They might have interior, they might not have interior. That's a huge section of this parameter space we know nothing about. Okay. Points of uniqueness. So we'll say a point xy is a point of uniqueness if it has a unique address with respect to the contraction map. So I've got a map F1, F1 and F2. So I would look at like F1 composed with F1, composed with F2, composed with F1, and if I get an infinite chain, that actually corresponds to exactly one point, because that's sort of an infinite contraction. And sometimes these will have multiple ways of representing the point, sometimes there's only one way to represent the point. So as a simple example, if a point is both in the image of K from F1, or the point is in the image of K from F2, well, it definitely has 2 representations, because it has a representation that starts with F1 and a representation that starts with F2. So it can't be a point of uniqueness. If the iterative function system is totally disconnected, this means all the points that start with F1 or F1 of K are completely disjoint from all the points in F2 of K, and hence you can't possibly have any points that have the same address, because they couldn't have the same address at the beginning. If you had something smaller down here, you just sort of take off the first couple terms until they're different. So there's some places where it's the same, some places where it's different. The question we were asking with, or the question we were saying is, what can you say about this set of uniqueness? Turns out the set of uniqueness is not empty. So there's a bunch of points that will have a unique address. Not only is it non-empty, it has positive Hausdorff dimension. And it's nowhere dense. So despite having positive Hausdorff dimension, it's still sort of dust-like. I want to give a quick sketch of how you get positive Hausdorff dimension. And again, the idea that I'm doing here is for the positive case. Very similar things happen for the negative case and the Jordan block case, and everything breaks for the complex case. So what we do is we look at this iterative function system, and as I said before, we could figure out something about this convex hull. We can actually figure out exactly what these points are. My notation here, p to the infinity is actually f1 composed with f1 composed with f1 an infinite number of times. M times p to the infinity is f2, then composed with f1, f1, f1 an infinite number of times. And all of these points here are points in the iterated function system, and they have a unique address. So that gives us a countable number of unique addresses, not enough with positive Hausdorff dimension. But using these points, we can construct an L so that any map of this form, or any point of this form, p to the k1, m to the k2, p to the k3, m to the k4, and so on, where these ki's are sufficiently large, then they're going to have unique addresses. So what I'm saying is somehow it's sort of catching all the tops of all these points and maybe these points down here. So you just take a lot of positive, then a lot of negative, then a lot of positive. And using this set is actually going to have positive topological entropy, and hence it's going to have a positive dimension. As I said, everything breaks for the complex case, and it's just because of the complex case. If the angles are somehow irrational that you get from the eigenvalues, everything is good because you actually have the same sort of extreme points, and you get a infinite number of them, and you can use them for a topological entry sort of argument. If these are a third of the circle, or rotating by a third, or rotating it by a quarter, everything breaks. And it's just because things line up too nicely and you don't have the same number of points on the end. So if it's this argument of a plus bi over pi is irrational, we get the same property. The set is non-empty. Well, the set's actually going to be non-empty in both cases. The next parts are positive topological entropy, positive Hausdorff dimension. That's going to happen if it's irrational. If it's rational, there's cases where it can happen, it's cases where it can't, but it's a much more complicated idea. So some things that still not quite sure how to answer, which we think are interesting, is when we want to see if the iterated function system contained any interior, we cheated and said that is 0, 0 in the interior. I don't know if those are equivalent. It's entirely possible that there is some iterated function system where 0, 0 is not in the interior, but it still has meaningful interior. Does it exist? You can have these points of uniqueness. All the points on the positive case and then a mixed case and such tend to be on the boundary. Is it possible to have a point of uniqueness in the interior? It is possible in the complex case. I don't know if it's possible in any of these other three cases. As I said, we talked about when is the iterated function system connected or disconnected. That was the question I raised, but we actually did much the same analysis there. But there's a difference between being connected and being simply connected. Simply connected means you can't do any loops that are around things that aren't in there. I have no idea how to even figure out what I would have to check to see if an IFS is simply connected. And we're going to end slightly early.
Any questions?
Yeah.
So I assume that these questions are independent of what the translational parts of the affine.
Yeah, it's actually independent of the translational part.
Okay.
So long as the translational part is not stupid, it's a bad way to phrase it, but for example, if I translated the x direction and nothing in the y direction for both parts, then the whole thing gets compressed to a line. But so long as these vectors are somehow reasonable, then the IFS you get is just going to be a contraction or expansion in some direction or the other of the other IFSs. So it's independent of the vectors.
And with respect to the question of interior, so if you hold one of the eigenvalues constant, like you did in your slide there, and you vary the other, let's say in the positive case, and you vary the other, is there a threshold? I mean, is it no interior and then there's a single, and then it's interior, there's interior after
I don't
that?
know. It's entirely possible that it goes in and out of having interior. I don't know. Like, the bounds we have on the interior is coming from a polynomial, but that's not the best way to do it, and it's really sort of an ad hoc method that just happens to work. But I'm not, unless you actually said, here's the lambda, here's the mu, you might be able to figure it out for that one, but I'm not sure how you would figure out for a parameter space. So it's possible that there's some sort of nice transition. It's possible it's some sort of goes in and out of that transition. I'm not even sure how to find it. I'm not sure at what point you could say, well, all of a sudden it doesn't have interior, or sorry, if it still has interior, can I lose 0 but still have interior? I don't know any of those things. Yeah.
I was just curious, so the 2 map, obviously this plays a big role. What sort of a role does it play, the fact that you have 2 translations?
I'll go back quickly. It's the fact that there's 2 is simply because it's you can't have 1 without having it being stupid.
Sure.
And 2 seem to be the next simplest
No,
case.
absolutely. But in terms of the proofs and in the results, how important was the fact that you had 2?
For some of the results, you could probably get away with 3 or 4. I mean, really what, for some of these results, is you explicitly wanted to figure out what the convex hull was and figure out the addresses for those outside points. And if you had more maps, you might be able to do something. It would be a lot more work, and you'd have to redo everything, but it should be doable. But I think our philosophy on this is, if we can't do 2 cases,
absolutely.
we didn't want to go to 3 or 4. And somehow 2 encompass a lot more structure than we expected right away. Should comment, a lot of this stuff we also did from, instead of R2 to R2, you can go to Rn to Rn, and a lot of this sort of analysis goes through. Other questions?
Thank you.